This is going to be another video where the presentation is text heavy and then the work is done in Excel. We're looking now at Runge-Kutta methods, and this is a generalization of Euler's formula. Y sub n plus 1 is equal to y sub n plus h times w1k1 plus w2k2 all the way to wmkm, and the k's are slopes. Like before, we said that y prime was equal to f of xy, and that was our k1 when we were using Euler's method. K2, using the improved Euler's method, was f of x sub n plus 1 y sub n plus 1 star, and that was another slope. Now, instead of considering an average of two slopes, we're considering a weighted average of k slopes. The weights w1 through wm add up to 1, and as we saw with the improved Euler's method, the k values for the slopes are recursively defined. M is the order of the method, and that's referring to how many slopes we're using. When we saw Euler's formula, or Euler's method, the first time, m was 1, we only used one slope, the weight was 1, and k1 was f of x sub n y sub n, like I wrote up here. Euler's method is a first-order Runge-Kutta method. Since m is the order of the method, a second-order Runge-Kutta method would use two slopes. And we saw that with the improved Euler's method. I won't hold you to any of these details, but I do want you to have a little bit of foundation here. Y sub n plus 1 is equal to y sub n plus h, the step size, times w1k1 plus w2k2. In this case, k1 is f of x sub n y sub n. We saw that in Euler's method first of all. And then k2 is f of x sub n plus alpha h, y sub n plus beta h k1. So the output from k1 is going into the formula for k2, and we saw that again exactly when we used the improved Euler's method. If w1, w2 add up to 1, and w2 alpha is 1/2 and w2 beta is 1/2, then we end up with something that agrees with a second-degree Taylor polynomial. Particular choices for w2, w1, alpha, and beta give us the results that agree with the improved Euler's method. Again, I don't really want you to focus on all those details. I want you to focus on that structurally we are getting an approximation for a y value using a weighted average of slopes, and that the second slope was obtained after we got the first slope. There does exist a third-order Runge-Kutta method. We're not going to look at it. We're going to look at what's called a fourth-order Runge-Kutta method, and this is actually what we're going to use when we get to Excel. It's abbreviated RK4. That's something you can see out there if you see like numerical solvers. An RK4 method uses a weighted average of 4 slopes. A lot of details here. What I want you to get is y sub n plus 1 is y sub n plus h times a weighted average of 4 slopes, w1k1, w2k2, w3k3, plus w4k4, all added together. K1 is f of x sub n y sub n. Now that's going to come from the original differential equation, just like we saw in Euler's method. K sub 2 is this formula. It's rather complicated, but we need k1 in order to get k2. We need k2 and k1 in order to get k3. And we need k3 and k2 and k1 in order to get k4. In order to make this formula agree with a fourth-degree Taylor polynomial, we end up with a system that has 11 equations and 13 unknowns, which means there are parameters and the system doesn't have a unique solution. In other words, there's a choice that can be made, and folks have made this one particular choice to give us y sub n plus 1 is equal to y sub n plus h over 6 times k1 plus 2k2 plus 3k3 plus k4. I'm going to pause there. Notice the weights inside the parentheses would be 1 plus 2 plus 2 plus 1. That's 6. We're dividing by 6 here, so all the weights add up to 1. K1 is what it always has been. K2 is f of x sub n plus half h, y sub n plus 1/2 of h times k1. And then we see similar formulas for k3 and k4. k3 is f of x sub n plus 1/2 h, y sub n plus 1/2 h k2. And k4 is f of x sub n plus h, y sub n plus h k3. You'll notice that some of the coefficients turned out to be 0 for this method. I suppose I should point out this is like one RK4 method, but it's a pretty common one. Not the RK4 method. Anyway, local and global truncation errors using RK4 are big O h to the 5th and big O h to the 4th, respectively. That means that the global error is on the order of h to the 4th. And remember that using Euler's method, the error is big OH, and improved Euler's method gives us an error of big OH squared. Since h is really small, h to the 4th is much better. I know that was all pretty dry. We are now going to see what using this set of formulas looks like. What we need is an f of x sub n, y sub n, an initial value for x naught, y naught, and a step size. Use the RK4 method with a step size h equals 0.1, and we're going to get a 4 decimal approximation to the value of y of 1/2 when our slope is given by y prime is equal to 4x minus 2y, and the initial condition y of 0 is equal to 2. You'll notice this is an example that we saw previously. We used the improved Euler's method, so second order Runge-Kutta. And here we're going to see what the difference is in the error and I guess the process as well. I've got Excel fired up. We have our step size of 1/10, x sub n, y sub n, and then I've already entered k1, at least as a header. And we of course need k2, k3, and k4. Initial conditions: when x is 0, y is 2. We need to fill in our x values, so we'll say that our x value is equal to a previous x value plus our step size of 1/10. We'll lock that in, absolute referencing, and then drag that formula down till we have 0.5. Now for k1, which is f of x sub n, y sub n, we have the equation here, 4x minus 2y. So that's going to equal 4 times x minus 2 times y. Now notice that k2 has the structure of f, but instead of 4x minus 2y, it's 4 times the quantity of x sub n plus 1/2 h, minus 2 times the quantity of y sub n plus 1/2 h k1. So what I have for k2 in here is equal to 4 times x plus 1/2 h. And when I'm using h, it's absolute referencing, you note the dollar signs, end parentheses, minus 2 times the quantity of y plus 1/2 times h, absolute referencing, times k1. Get that in there, and then move on to k3. k3 and k4 have similar formulas, so I'm just going to go ahead and fill those in. Now, having entered in formulas for k1, k2, k3, and k4, we're going to find y sub n plus 1. It is equal to, and I'm looking at the y sub n plus 1 formula here, y sub n plus the step size 0.1, absolute reference, divided by 6 times the sum of k1 plus 2 times k2 plus 2 times k3 plus k4. And then I can drag down the formulas for the k's and then grab the y and the formula for the k's, drag that down, and we get an approximation for y of 1/2. Now we saw in the previous set of videos how to compute the error table here. And what we see is a percent relative error using a step size of 1/10 of 0.001576. If you reference the previous videos, this is a much smaller error. I mean, even using the improved Euler's method, that was like 0.78%. I also went ahead and computed all this using a step size of 0.05. And I again would like to point out the relative sizes of the relative percent, or the percent relative errors. when h is 0.05, the percent relative error is 0.000091%, right? And I actually computed this. If you take 0.001576 and divide it by 0.000091, you get about 17. Now, we were told that the error using an RK4 method is big O h to the fourth. What we did was we cut the step size in half, and the error was reduced by about a factor of 16. I mean, it turned out to be 17, but again, it's in the ballpark.